Hi everyone, today we're looking at waves and energy transfers. We came down to the wonderful Sheila's Beach to have a look at this. A wave shows the transfer of energy without the transfer of matter. When we're looking at waves, there are two different types. There's transverse waves, of which water waves are an example, and longitudinal waves, of which sound waves are an example. Transverse waves have got very clear peaks and troughs. So that's a transverse wave, where the top of it is the peak and the bottom of it is the trough. Here we can see the two different types of wave. We've got a transverse wave and a longitudinal wave. When we're looking at these, we can see some key characteristics. At the top of a transverse wave, we've got a peak, and at the bottom, we've got a trough. Distance between two identical points on a wave is called the wavelength. And we'll find this in transverse and longitudinal waves. So that's the wavelength, which we represent with this symbol for lambda. The amplitude is the height of the wave from the middle of the line to the top of the peak. Looking over here at the longitudinal waves, where all the particles are clumped together, it's what we call the compression. And where the particles are all further apart, it's what we call a rarefaction. So there we've got our transverse and our longitudinal wave. Water waves can be used to model the transverse wave, with peaks when they rise and troughs when they fall. Sound waves, however, are examples of longitudinal waves, where the wave vibrates in the direction of propagation. Look at frequency. Across the top here, we've got some different intervals in seconds. So that's 1, 2, 3, 4, and 5 seconds. If we were to have a wave with a low frequency, it might take 5 seconds for one whole wave to pass. If we were to see a wave with a higher frequency, you can see that 2 waves have passed in the space of this time. What we've got here is a very crudely made wave machine. We've got a fixed point at either end, we've got some gaffer tape running throughout, and some cocktail sticks with midget gems on. What we can show with this is a transverse wave. A transverse wave is where the medium vibrates at right angles to the direction of propagation. We can see when we lift this up, the energy is transferred along and back, but the medium, the midget gems, move up and down. We can observe the midget gems moving up and down at right angles to the direction of the propagation. This can also be seen with seabirds bobbing up and down in the water and not moving in the direction of the wave towards the shore. One thing we'll do with this is change the amplitude or the height of the wave. When we move it like that, the amplitude isn't as great as if we were to take the midget gem and move it all the way up like that. But you can see that the amplitude of the second wave was higher. When we're studying waves, we can use what we call the wave equation. So the wave equation uses 3 things. It uses the speed of the wave, which we're going to call velocity, or v, and that's measured in meters per second. We're going to look at the frequency of a wave, which is how many waves pass in a certain time interval. So that's the frequency, and we measure frequency in hertz, H to Z. And then finally, we're going to look at the wavelength, and we use this symbol for lambda. And you can measure the wavelength in any unit of distance, but when we're looking at this, we're going to use meters. You can use these together in an equation triangle. So wave speed is equal to frequency times by wavelength. Thanks for watching today's lesson, everyone. Today we've looked at waves, the difference between transverse and longitudinal, how to draw and label a wave, and how we can use the wave equation as well. Thank you very much, enjoy your weeks.